let's take a look at that previous example where we found the derivative, so we know what r prime is. And let's use Maple to do some plotting for us so we can take a look and try to make a little bit more sense out of what's actually happening. To do it on paper and have a bunch of numbers in front of you is one thing. To actually see it is yet another. So let's bring up Maple. And I have all the commands set up in a worksheet. I'm going to see if I can't make this a little bit bigger so you can see it. Maybe go to there. Okay. Which I will probably make that worksheet available to you in class. Otherwise, here's all the commands for it. You may want to pause so you can type them in. Watch out for typos. So I need with plots to give me a bunch of stuff. I need student vector calculus. And then what I have is I have two space curves set up as a and b. This is our original function, a, and b is our derivative function. I made them kind of thick, set the thickness to 4 so I can see them a little bit better. And then I set k equal to 3 pi over 4 only because that allows me to play with it a little bit, and I can just change this value here once k, and then it automatically goes into like 1, 2, 3, 4 different places. So let's go ahead and just plot this thing and see what we get. Okay, that looks cool. Let me explain to you what's going on here a little bit. Let me make this a little bit bigger. Okay, this red curve is our space curve. This black curve is our prime of t. So it's the derivative curve. And this red vector is simply the position vector to the point where t equals 3 pi over 4. This black vector is a position vector on the derivative space curve to where t equals 3 pi over 4. So if we look at this, let me spin this thing around a little bit. And I'm going to try to convince you of something here, if you can visualize this. That's not too bad. Okay, so I'm interested in this point. Now, just simply by looking at this point, forget about the black stuff for a moment. Pretend like the black curves aren't even there. Just by looking at this point, if I gave you this graph and I said, hey, just hand draw in what you think the tangent line is, you're all going to make a tangent line, you know, through like this, because you know what it means to be tangent. But notice when you draw that line, that it's essentially, visually, it appears to be parallel to this vector line. This is r prime of t, where t equals 3 pi over 4. Or if you look back in your notes, that is the position vector, negative root 2 over 2, negative root 2 over 2, 2. It's not 1 over root 5 times that. That would be the unit vector, which I could do for you very quickly if you wanted to. Let me take a look here real quick. Okay, c, because it's in black, and right there is my derivative. That is the black vector. So if I just simply take, I've never done this, but I'm sure it'll work. If I take 1 divided by square root of 5, that should multiply by that vector. So I should now have, yep, let me make it bigger. I now have the unit vector. So that has length 1, which may or may not be easy to convince you that has length 1, but it does. But see, it's still pointing in the same direction, and it's parallel. It's still a direction vector for the line that would be tangent at that point, 3 pi over 4. So you may want to enter that in Maple and fiddle with it a little bit and kind of see what you can come up with. I just replotted it, taking out that 1 over root 5. But anyway, you spin this around and think about it and put in different values. That's why I put this k up here like this. What if I made this k, I don't know, how about just pi over 2? You know, it looks very similar, obviously, but it's just a different angle. But still, you can see how this would be parallel to the tangent line. Now, let me ask you something. Think about this and talk about it in class. Are these two vectors orthogonal? Should they be And are they orthogonal? There's something for you to think about.